coming to the problem statement. So here you are going to determine the support moments for the continuous girder. Girder means beam, as shown in the figure by using a slope deflection method. So if the support B sinks by 5 mm, and here you are going to take for all the members EI is constant, whereas the value of I and E has been given here. I is equal to 4 into 10 power 7 mm per 4 and E is equal to 200 kilonewton per mm square. Now we'll see the figure. So here you can see. So in this figure, what is given is at B, the support has been sink by 5 mm. So here this is 5 mm. So it has been, the new place of the B has been shifted to B dash. So here B dash is 5 mm. And here E and I is also given. So just I'll convert here. So EI will be equal to 200 into 4 into 10 power 7 kilonewton mm square. So that means it will be equal to 8,000 kilonewton meter square. So EI you can take it as 8,000 kilonewton meter square. So here only we are just converting. Okay. So next. So coming to your first step, you can see here, first step, you are going to determine your degree of freedom. So determine the degree of freedom. So here at A, you can see that the support is a fixed support. So for this support, there will be no translation and there will be no rotation. So that means here theta A is equal to 0 and delta A is also equal to 0. Now coming to the B support, here there will be a rotation, but already theta B not equal to 0 and delta B is given as 5 mm, already the settlement. And now coming to the C part, there will be a rotation. So that means theta C is not equal to 0. And whereas delta C is equal to 0. Why? Because there is no translation here. Similarly, the D support is also a fixed support. Therefore, the rotation and translation both are 0 here. That means theta D and delta D is equal to 0. So for this case, the degree of freedom is equal to 2. So that means theta B and theta C are your unknowns, and you're going to find these two unknowns by using this slope deflection method. Now coming to your next step. So here you are going to calculate your fixed end moments for this beam. So first you're going to consider the span AB. So here the span AB has been considered. And the span, the loading here is 50 kilonewton per meter UDL and the span is 4 meters. Now here you can see that we consider the support, both end supports to be your fixed end supports. And here you are writing the fixed end moments. So fixed end moments for A, it is anti-clockwise direction. Therefore, it is in negative sign. And whereas for BA, it is in clockwise direction. Therefore, it is positive that has been given. So the sign convention in your slope deflection method is you're going to consider clockwise moments to be positive and anti-clockwise moments to be negative. So these are the fixed end moments formula that has been used when you are having a UDL. So this is WL square by 12 and this is also WL square by 12, but it is of opposite signs. So when you use these equations and when we find the fixed end moments, so you are going to get these values, MFAB and MFBA. This is for the first span AB. Next span BC we are going to consider. So BC here we are having a point load. So which is at the center, the load is. So total span is 2 meters. So as we are having a point load at the center, the fixed end moments that are going to develop at B and C are WL by 8 only. So, but whereas here it is at B point, it is in anti-clockwise direction. So it is negative. Whereas at the C portion, it is in clockwise direction. Therefore, it is positive. So now you're going to calculate MFBC and MFCB. So these values are minus 25 and plus 25 kilonewton meter. So this is for the span BC. Again, you're going to do it for the CD span. So CD span also, again, you are having a UDL, so which is of 5 meters. And for this also, as it is a UDL, you're going to have the fixed end moments as WL square by 12 at each end. So that C, it is in anti-clockwise direction, at D it is in the clockwise direction. Therefore, you are going to get your moments MFCD and MFDC, that is fixed end moments, that is minus 83.33, and next is your plus 83.33. So these are the calculation of your fixed end moments. So by using these fixed end moments, in the next step, you are going to substitute in the slope deflection equations. So in this case, for calculating the fixed end moments, you are going to assume all ends to be a fixed. I mean, all supports to be a fixed supports. So by assuming that only, you are going to calculate this fixed end moments. So this is your second step. Now coming to your third step, so that you are going to use a slope deflection equations. So for this beam, so this is a generalized slope deflection equation. So for this, what we are going to consider is, for suppose if you are considering AB span, so the B support has been sunk by 5 mm. So that means here delta you are going to consider as 5 by 1000 meters. Okay. 5 into 10 power minus 3 meters you are going to consider, and you're going to substitute for AB span and BA span. So here the settlement will be positive for AB. So now you're going to substitute here. And one more thing is, here A support is fixed support. Therefore, the theta A will be equal to 0 for this case. And then by substituting all these values here, the span 4 meters, EI is EI only, then the delta is 5 by 1000. When we substitute all this, you're going to get simplified equation in this manner. And similarly, MBA also. So here also theta A is 0, delta is equal to 5 by 1000 meters you're going to substitute. And in the next equation, you're going to simplify. And finally, you're going to get MBA as EI into theta B plus 51.67. So this is your next one. Similarly, when we do it for the BC span. So BC span means here what is happening? So here, what is happening is, so the support has been so here when we consider this, so for BC, so the delta will be equal to minus 5 by 1000 meters. Similarly, for BC and CB span, it is a negative displacement. So here this displacement will be negative for BC and CB. So you're going to substitute the negative value for the delta for the BC span. So when we substitute this equation, so you're going to get this equation value. And similarly for CB also, when you substitute here, you're going to get the equation, final equation for MCB will be like this. So after simplifying this MCB and MBC, then we move to the next span, that is your CD span. So for CD span, as there is no displacement at C and there is no displacement at D, so here what is happening is delta will be equal to 0. And similarly, as there is a fixed support at D, so here theta D is also equal to 0. So now you're going to use all these values and you're going to substitute here. Already we found the fixed end moments in the earlier slides. So that you're going to substitute, and finally the equation will become like this. Similarly for MDC also, the equation is like this. So here also the theta D will be equal to 0, and whereas delta will be equal to 0. So by simplifying this equation, you're going to get MDC value to be like this. So this is another equation. So these all are the equations with the values that we know, we substituted in the slope deflection equation. So this is your step 3. Next, after this step 4, you are going to use the equilibrium equations. So what is your equilibrium equations? So here we are having B joint and C joint. So at B joint, there are two members joining, that is BA and BC. Whereas at C joint, there is CB and CD joining at that member, at that point, at that joint. So here we are having two equations. So that is sigma MB equal to 0. That means here two equations, that is sigma MB equal to 0 and sigma MC equal to 0. That means MBA plus MBC will be equal to 0. So from slope deflection equations, we are going to substitute MBA value and MBC value. Then you're going to get this equation. So here we are going to substitute in the place of EI also 8000 kilonewton meter square. And finally, you're going to get this equation 1. Similarly, second equilibrium equation is sigma MC equal to 0. That means MCB plus MCD will be equal to 0. So by using previous slope deflection equations, you are going to substitute here. And by simplifying this, you are going to get this equation 2. So by solving these 1 and 2 equations, you are going to get theta B to be a negative value and theta C to be a positive value. So negative means you are getting in an anti-clockwise direction, whereas positive means you are getting a clockwise rotation. So this is how you are going to determine the rotations. Okay. So by using these rotations, you are going to draw the elastic curve. So here for drawing an elastic curve, so theta B value is this and theta C value is this. So for this beam, I'm going to draw the elastic curve. So this is A support and this is B support and this is your C support and this is your D support. So for suppose if you are drawing the curve towards downward, when we draw a tangent and we make a angle here, so it is in anti-clockwise direction. So therefore it is right. So your curve will be like this. Again, it is going to go up. Again, it is going to come down. And then here delta D will be equal to 0. So here we know theta A equal to 0 and theta D is also equal to 0. Whereas at B, when we draw a tangent, so it is in anti-clockwise direction. Therefore, theta B will be equal to, you no need to write here sign, 32.56 by EI. So it is in anti-clockwise direction. So here the sign convention is clockwise direction rotation is positive, anti-clockwise rotation is negative. So here also when we draw a tangent at C, so here we are going to get in the positive way, that is clockwise direction. So that means theta C will be equal to 11.03 by EI. So here EI also you can substitute, but I'm not just substituting, we can simplify it. So that we can, it will just get cancelled in the slope deflection equations. So that is the reason I am leaving EI here. So this is how you are going to draw your elastic curve. And next is your calculation of your final end moment. So for calculating final end moments, so here we are using the theta B value. Okay, so theta B and theta C have written here just typographical mistake. So I'll just correct it down. So theta B is 32.56 and theta C is 11.03. So here theta B is equal to 32.96 and whereas theta C is equal to 11.03. We'll just see the sign convention also. Okay, minus 32.56 and plus 11.03. So this is how you're going to substitute these values. So by substituting these values, you're going to get your final equations to be MAB is minus 97.95 kilonewton meter and MBA is 19.11 kilonewton meter and MBC is minus 19.09 kilonewton meter and MCB is plus 74.5 kilonewton meter. MCD is minus 74.5 kilonewton meter and MDC is 87.742 kilonewton meter. So these are your final end moments by substituting these values. So for drawing a bending moment diagram, we'll just place all these moment values here. Okay, we'll place all these moments. Then we are going to draw the free body diagram for this first. So first I will draw the figure. So this is a beam. Here you are having two supports. And this loading is 50 kilonewton per meter, which is of 4 meters for AB span. And for BC span, you are having 100 kilonewton, and this is 1 meter and this is 1 meter. So total 2 meters. And again, here you are having 40 kilonewton per meter, so which is of 5 meters. So for this, we'll first draw the free body diagram. So here A, B, C, and D. So AB moment is negative. So it is in anti-clockwise direction of 97.95 kilonewton meter. And BA, you are having again a positive, that means clockwise. BC again negative anti-clockwise. So that is 19.1 kilonewton meter. And CB, it is positive, that means clockwise, and CD is negative, that means it is anti-clockwise, so that is 74.5 kilonewton meter. And similarly, MDC is again positive, so that means it is a clockwise of 87.742 kilonewton meter. So this is the external moments, I mean end moments that we got, and this is an external load I'm just drawing. So for this, you are going to draw the bending moment diagram. So how you're going to draw your bending moment diagram is, first I'll draw the simple bending moment diagram. So for AB, as you're having UDL, so for UDL simply supported, it is like this. So that means here the value is UDL 50, so WL square by 8. So that means it is 50 into 4 square by 8. So this will be around 100 kilonewton meter. Okay. Similarly, here also it is WL by 4. So that is 100 into 2 by 4. That means it is a 50 value. So WL by 4. So that is 50 kilonewton meter. Again, it is WL square by 8. So WL square by 8 is again 40 into 5 square by 8. So that means 125. So this is again, so 40 into 5 square by 8. So this 5 times. So it is 125 kilonewton meter. So these all are your simple bending moment diagram when you're having an external load and the reaction. So for this, it will be a bending moment diagram. So to this, what you're going to draw is you're going to make a conversion with this final end moment. So it is 97.95. So which is in hogging in nature. So negative. And it is 19.1. So it is 19.1. Again, it is 74 point something. So it will be like this. And it is 85. So it will be also around something like this. Okay. So for this, it is 90 around. Join like this. Again, it will be like this. Again, it is something like 70. Okay. 1 second. So it is something like 74. Okay, it is 74. So it will be like this. Again, it is of something like 87. So these all are negative values. So this is 74.5 kilonewton meter, and this is 87.7 kilonewton meter, and this is 19.1 kilonewton meter, and this is 97.95 kilonewton meter. So these all are your negative values. So your final bending moment diagram will be like this. So the resultant bending moment diagram. So here what we have drawn is, we first draw the parabola for this UDL loading, and for this it is a triangular load. Again for this it is a parabola. So this is all for your simple bending moment diagram. Then coming to your fixed moment values. So for this fixed moment values, so these all are hogging in nature. So this will be a negative. So the conversion, the intersection of these two is going to become a final end bending moment diagram. So this is how it is going to look like. The shaded portion will be your final bending moment diagram. Next, we are going to see the shear force diagram. So for the shear force diagram, again I'll draw the figure. So this is A support, B support, C support, and D support. So for AB span, it is of UDL, so which is of 50 kilonewton per meter, which is of 4 meters. And for BC span, it is 100 kilonewton, so which is of 1 meter, 1 meter, so it is 2 meters. Again for CD span, it is 40 kilonewton per meter, and it is of 5 meters. So for this, we are going to draw a free body diagram for AB, BC, and CB. So for AB, it is 50 kilonewton per meter, and it is 100 kilonewton, and it is 40 kilonewton per meter, which is 5 meters, and this is 2 meters, and this is again 4 meters. So MAB moment you are getting anti-clockwise of 97.995 kilonewton meter, and here at this is A, B, C, and D. At B point, you are getting a 19.1 kilonewton meter, and at C point, you are getting 74.5 kilonewton meter. Again, at the D point, you are getting 87.74 kilonewton meter. So for this, you are going to first find the reactions. So this is your RA, and this is your RB1, and this is your RB2, and this is your RC1, and this is your RC2, and this is your RD. So coming over to this span, so I'm just taking moment about A will be equal to minus 97.95 kilonewton meter. So that means moment about this point I'm taking. So now what I'm going to write is RB1 into 4, okay, minus 19.9. So that is moment at this point, minus this 50 into 4 into 4 by 2 will be equal to minus 97.95. So that means RB1, you're going to get it as 80.28 kilonewton. Whereas coming to your RA, so RA will be equal to 50 into 4. That is total load acting on this beam minus 80.28. So finally, you're going to get 119.7 kilonewton. So this is your RA. Similar way, here also moment about B I am taking at this point. So that will be equal to minus 19.1 kilonewton meter. So moment about this point I'm taking. Similar way, RC1 into 2 minus 74.5 this moment minus 100 into 1 will be equal to minus 19.1. So RC1 will be equal to 77.7 kilonewton and RB2 plus RC1 will be equal to 100 kilonewton. So this implies RB2 will be equal to 22.3 kilonewton. So this is another one. Next, coming to here, moment about C. So that means this point, moment about C will be equal to minus 74.5 kilonewton meter. So that means moment about this point means RD into 5 minus 87.74 minus 40 into 5 into 5 by 2 will be equal to minus 74.5. So here RD will be equal to 102.65 kilonewton meter. Now RC2 plus RD will be equal to 40 into 5. So this implies RC2 will be equal to 97.35 kilonewton. So this is your RC2 value and this is your RD value and this is your RB2, RC1 and RB1 and RA is equal to this value. So after getting all these values, as the all are getting positive, so the reactions are the same, that is upward only. Now to draw a shear force diagram, so here as it is a UDL, so RA is 119, RB1 is 80.28. So this is one. And RB2 is here again point load. So it is 22.3 and again here you are getting 77. Again RC2 you are getting 97. Again RD you are getting 102. So I'm just writing the values. So this is 119.7 kilonewton. This is A point. And again RB1 you are getting 80.28 kilonewton. And this is positive. Again this is negative. At C point you are getting again 77.7 kilonewton. And RC2 you are getting 97.35 kilonewton. And at D you are getting, sorry, this is positive. And this is negative of 102.65 kilonewton. So this shaded portion is your shear force diagram. This is how we are going to calculate the shear force diagram. I hope it is clear. So just simply as a simply supported shear force diagram you are going to draw, but you are going to calculate reactions with the help of the end moments also. These are the references. Thank you.